Good morning, everyone, or good afternoon for those of you in Europe, which is pretty much everyone. I am Scott Will. I'm a PhD student from the University of Rochester in the USA, and I will be talking about a more computationally efficient approach to model-based wavefront control. I added this asterisk here for choreography. It did not occur to me to specify that in my title when I originally submitted, but there's been a lot of discussion this week on real-time wavefront control among many of the participants. So here's my obligatory science context slide. Much of this will be familiar to you. So since 1992, the scientific community has discovered more than 4,000 exoplanets, mostly through indirect methods like transits and radial velocities. But future missions, direct imaging missions such as HABEX and LUVOIR, will attempt to use direct imaging to directly detect and characterize Earth-like planets around Sun-like stars. And this is a very, very challenging problem because it requires starlight to be suppressed by a factor of up to 10 to the 10 at very small angular separations. Now, in choreography, we usually operate, especially in space-based choreography, in a very small wavefront error regime. But even in this regime, the dark zone where we hope to detect a planet is dominated by this kind of long-lived quasi-static speckle from diffracted starlight that results from wavefront errors on the various optics in the optical train. But it turns out that there's a very useful approximation here where the electric field at the detector can be linearly decomposed into a term from the aberrations and a term contributed by the DMs. And we use this linear approximation to derive focal plane wavefront estimation algorithms that directly estimate the electric field at the detector. And this eliminates non-common path aberrations, which is extremely useful. And then also critical is closed-loop wavefront control that iteratively minimizes this quasi-static speckle that's coherent with the star using two deformable mirrors, usually one in the pupil plane and one out of pupil, which correct amplitude and phase aberrations over a two-sided dark zone. And these control and estimation algorithms iterate back and forth between one another so that we iteratively minimize speckle. Now, one very common approach to chronographic wavefront control in closed loop is the stroke minimization algorithm, where we attempt to find the smallest actuator command update that causes the integrated intensity from the star in the dark zone to dip below some target value. And the way that this is approached currently is through the method of Lagrange multipliers, where this objective function is relaxed into a scalar Lagrangian, and then we attempt to find its critical points. So what we conventionally would do would be to use a numerical model of our instrument to evaluate this Jacobian matrix, which is the derivative of the electric field at the focal plane with respect to our actuator commands. And then given this Jacobian, we have a nice analytic expression for the optimal actuator updates as a function of the Lagrange multiplier. And then what we do is generate a family of solutions for actuator commands with different values of the Lagrange multiplier and choose the smallest value such that our constraint is satisfied. The trouble here is that in order to do this, we have to calculate this Jacobian matrix, which is a matrix value derivative, and this is extremely computationally expensive. So usually what we do is just pre-compute a Jacobian matrix using, for example, a flat set of DM commands before we start our experiment, and then reuse this matrix for many iterations. This is fine, but it reduces the speed that we converge to very high contrast. And additionally, for broadband observing scenarios where we need to control multiple wavelengths, we need to compute a separate Jacobian matrix for every wavelength that we hope to control. So is there a better approach here? And the answer is yes. The approach that I took was using what's called reverse mode algorithmic differentiation, or RMAD. This is a framework for efficient analytical differentiation of numerical algorithms. And by that, what I mean is a sequence of n differential operations with the final variable being scalar. So for example, the objective function for an optimization problem. Now, the main idea is, given this forward model or algorithm, we construct an adjoint model which evaluates the derivatives of the final variable, which is scalar, with respect to each of the intermediate variables in the forward model. We can do this manually, which means that the programmer or graduate student implements it, or the computer can do this automatically by transforming the forward model. The really key thing here is that using RMAD, the cost of evaluating a gradient is approximately the same as evaluating the forward model, which we call the cheap gradient principle. And I'll also note that RMAD is also known as the backpropagation algorithm. So those of you who work with neural nets, you probably have heard that name over and over again. So the proposed algorithm which I implemented is a variation of the stroke minimization algorithm that uses a quadratic penalty on the contrast. The reason is that in doing so, we can enforce the contrast target in each control iteration without a line search over the scalar penalty parameter. And then in each control iteration, we optimize the subjective function using nonlinear optimization with a very fast, efficient RMAD gradient. The advantages here are that we don't have to compute a Jacobian matrix at all, which massively reduces the amount of upfront computation required for wavefront control. And it also makes it very easy to update our model in between control iterations. And this algorithm only uses vector value derivatives or gradients during computation, which means it scales much better with actuator count, the number of actuators on the DMs, as well as the number of pixels in the dark zone. So now I'll show you some simulation results where I compared the proposed method to a conventional Jacobian-based algorithm using an apodized people-Leo chronograph design, which was submitted to the 2020 Astrophysics Decadal Survey for the LUVOIR mission. And I studied this, the two algorithms as a function of the number of actuators across the DMs. So here we have a 50 by 50 DM, which is kind of like a Boston 2K DM. It's approximately equivalent to it, as well, going all the way up to 128 by 128 actuators, which is what's baseline for the future LUVOIR mission. So both algorithms converge to 10⁻⁻10 contrast after 25 iterations, so that's nice. What I'm showing you here on the left is a plot of the online runtime as a function of iteration, where the Jacobian-based algorithm is in blue and the proposed gradient-based algorithm is in red. As the colors get darker, the number of actuators increases. So what we're seeing here is that for the lowest actuator counts, the Jacobian-based algorithm is a bit faster in runtime because we have an optimal analytic expression for the actuator commands. But it's very, very slow when the number of actuators goes up to 128 by 128, whereas the proposed algorithm's runtime is pretty much invariant to the number of actuators. Now, this does not factor in the time cost of pre-computing the Jacobian matrix for this Jacobian-based algorithm. So I'm just going to move on here to the memory usage, which is also very important. So now I'm showing you on the vertical axis the median and worst case RAM usage by each algorithm as a function of the number of actuators across one side of the DM. And what we see here, again, is that at the lowest actuator account, the two algorithms are very close in terms of their memory consumption. But when we move to 128 by 128, we're talking 35 gigabytes here. So that is a very non-negligible amount of RAM, especially for a mission using space flight qualified hardware. In this case, the proposed algorithm uses less than 10% of the memory of the Jacobian-based algorithm, which is a significant improvement in computational efficiency. And since this is only a 5-minute talk, I'll just talk a little bit about future work and then open to questions. So the very next thing I should say is laboratory demonstrations to show that this really does work in the lab. But there are actually some very neat things that this framework enables, first of which is a dynamically updated model. So I mentioned that we can update the model that we use for wavefront control in between iterations, and this allows us to capture time-varying effects in our system which are not accessible to a Jacobian-based method using a static Jacobian matrix. So for example, we could use data from a low-order wavefront sensor to capture low-order wavefront terms in each iteration. But Also, this opens new approaches to adaptive control. I, in this particular case, computed the gradient of the objective function with respect to the actuator commands, but we can just as easily compute gradients with respect to various model parameters and then use our measured control history to tune the knowledge of our model. And then by alternating between improving contrast and improving the model, ideally we would improve our convergence speed to high contrast. And with that, I will open the floor to your questions. Thank you for listening.
Okay, thank you, Scott. I think you're a little bit late here. You have a question from Carlos. You may check on Slack. I think maybe with